Probably more people will translate that. Thank you so much for having me this morning, Monday morning. It will be our last Fun Cafe this semester, and we're very happy to welcome Carson. He's a final year, or almost final year, student in our department. He's working under the supervision of Dr. Jesus Arroya, and today he's going to present his talk with joint work with Dr. Jesus and Dr. Gainanova. He's mainly working in network analysis, and before he joined Texas A&M, he got his bachelor's and master's degree in mathematics from Oklahoma State University. Let's welcome Carson, and thank you for featuring.
Thanks, guys. Yeah, so I'm just going to share some work we've been doing with you today. And yeah, so main idea, we're going to be talking about yeah, so yeah, we're going to be talking about like learning joint and individual structure with network data with covariates. This is a joint work with Dongbang Yuan and Irina Kainanova and my advisor, Jesus Arroyo. So, all right, let me kind of outline some like the general goal here for us. So we're in a setting where we're given multiple data sets. Each data set on a shared set of observations. So each data set is going to have some important information about what we're observing. And what we want to do is we want to isolate information that all the data sets are going to share. And then we want to isolate the information that's unique to each data set. And then once we have those, we can use those to ask or answer questions about like what each data set can tell us about the other, maybe give us a holistic view about what we're considering. And so we can ask questions like, for us, like we're going to be working with specifically a network. So that's one of our data sets. And then the other data set is, so network is just a collection of nodes. And then we're going to have some connectivity data about those nodes. So that's one data set. The other piece of information we're going to consider is at each node, we're going to go in and take some measurements. And we're going to record those as covariates. Okay, so it could be like height, weight, things like that for each person. And then connectivity could be friendship between people. All right, but we're going to be working with a data set, two data sets, connectivity and node covariates. All right, so the connectivity information is just going to be in the form of an adjacency matrix. So if we have n nodes, we're going to have an adjacency matrix that's in Rn by n. The ijth entry of this adjacency matrix is just going to indicate the connection strength between nodes I and j. Okay. The covariate data at each node, we're going to record, let's say, p covariates. All right. And so the ith row of our covariate matrix, it's just going to be that observation of p covariates for node I. All right. So both of these are going to contain important info about the nodes and relationships that they have. So which nodes are influential? What's any sort of community structure in the nodes? Like how do they group up? Maybe some nodes interact more or connect more strongly with nodes in the same group. So maybe you see groups of high connectivity. Maybe it's the opposite. Maybe you see nodes more connected between different groups and less connected within the same group. Also, the covariates that we measure at each node might contain information about similar things like maybe a little bit related to clustering or other pieces of relevant information. Okay. So just to give you guys a real data example, to have something in mind, this is something we'll circle back to, but you know, maybe we're interested in trade among countries. So each country could be a node. And then maybe we'll want to look at something that they trade. So we could look at food commodity trade between different countries. And then at each country, we can go record basic economic or geographical information like GDP, birth rate expenditure, and also what geographic region each country belongs to, things like that. Okay, so basically we've got two data sets on the same countries here, and then we're just asking questions like, okay, well, what can what can any sort of trade information tell us about what measurements we might observe at the nodes, at the countries, for this geographic and economic information. Go in the other direction, we might ask, like, okay, if we know the measurements for some covariates at all these countries, does that tell us anything about how they might trade? Maybe we'll see countries with high GDP trading amongst themselves, or maybe we might see trading blocks of low GDP countries. So anyway, yeah, and then yeah, okay, so maybe they also have information that they are shares that they share. So they might contain the same information, at least a part of it. Then they might, contain information that's unique to each. It's not accounted for by the other. Okay, so we would just like to have a holistic view of that data, and then maybe answer a few questions about that. Okay, good so far? Yeah. All right. All right, so we're about to start. I'll tell you the model here. But there's some related work on modeling joint individual structure. Generally, they fall into sort of three camps. Like the first one is a very popular when you have multiple covariate data sets. So this is it's a lot with like genome expression data, but basically multiple covariates, find out what they have in common, what's unique to each. You got like work like Jive, AJive, DMMD. The second camp is for multiple data sets. So there's some work about maybe shared structure among multiple network data where they share the same nodes. There's some work. There's some work that started a notion of shared and individual structure for multiple network data. And then lastly, you've got work addressing when your data sets are when you have a network data set and a covariate data set. But there's not a lot of work that treats shared and individual structure for networks with covariates. Okay. All right, so our model is pretty simple. It's going to be a signal plus noise model for the network and the covariates. Okay, so our adjacency matrix A, that's the connectivity that we observe. Our covariates X, they're both going to be a mean plus some noise. Okay, mean zero noise. And we need to make some assumptions about this structure. So we need to assume that these mean matrices are low rank. All right, so this is to avoid some trivial cases and for computation to be feasible. Also, we're going to need that the observed values are going to be close to their means. So I'll say more about that in a little bit later, but these are both pretty standard requirements. Maybe if you haven't heard about them, that's fine, but it may seem a little bit weird that you have a signal plus noise model for the network, like maybe you're considering binary data. But actually, a lot of models fall into this. So if you've worked with stochastic block model, which is just a model to capture community structure, or random dot product graphs, where each node has a latent position associated to it, and then the most general and homogeneous Bernoulli graphs. These can all be described with this. So it's not that weird. Okay. So now we've got our signal plus noise model. We want to define what it means to have like joint and individual information or structure or components, whatever you want to say. So what we're going to do is we're going to first define, given our means, our P and W matrices for the network and covariates, we're going to define the joint and individual subspaces as as the following. So the joint, you're going to take your P and your W mean matrices, and then we're going to form the intersection of their column spaces. So this is representing what they both have in common. This is the joint or shared bit. Okay, so once you have the joint, to get the individual subspace corresponding to the network, all you have to do is just take your mean for the network, so P, take that column space and then project onto the orthogonal complement of your joint. So it's everything else, it's everything in P that's not in the joint. So this is the stuff that's unique to the network, right? Do the same exact thing for your covariates. So you just take the stuff in the W column space, but just not in the joint. Okay, so it's unique to the covariates. So these are the joint and individual subspaces. Okay, so this is the first step. But once we have our subspaces, oh, and yeah, well, let's just denote the ranks of these subspaces by Rm for the joint and then Rk for the subspace script Rk. Just a note, by construction, the rank of P is going to be the joint part plus the individual for the network part rank, okay? And then same for the covariates. But okay, so like once we have our subspaces, we need some things to actually compute with. Okay, so we're going to get a matrix representation for these subspaces. So what we're going to do is we're going to choose bases. We're going to choose a basis of vectors for the joint subspace. So that's going to be, and then we're going to take that basis and stack them, or like row, column bind them. Okay, so this matrix M, that's going to be the matrix that whose column spaces are joint. Okay, but it's just it's an orthonormal basis in Rn for the joint subspace. Similarly, for the covariates, for the individual subspaces, we're going to get bases whose column space give us the individual subspaces. All right. And then once we get these components, the M and Rk, we can factor P and W like so. So P has this factorization where we've got the joint and individual components concatenated times some other stuff, okay? And then similarly, the covariate mean is joint component, individual component for the covariates times some other stuff that enjoy some nice properties. So let's see, full rank, okay. But then really important, the joint components are perpendicular to the orthogonal to the individual components, okay? And these matrices are unique up to orthogonal transformations. So really everything we're going to talk about is basically, it's going to be a stand-in for the subspaces. We care about the joint and individual subspaces, but for computation, we need some matrix representations for it. Since we're talking about the subspaces, these representatives are not unique. Okay? Any orthogonal rotation by right multiplication of say M will also give you the joint column space. Okay, similarly for the individual parts. So really we're talking about identifiability up to orthogonal rotation. Okay. So so that was the model. Let's kind of like talk about, let's just do like a simple example. So let's talk about like a network. There's 40 nodes. All right. Each node is going to belong to one of 4 groups. And then at each node, we're going to observe 3 covariates. Okay, so here's a little figure. So if you just forget about the color, just look at the shape here. The shape is capturing, the shape, you can see sort of 3 groups emerge just based on connectivity. You've got a group here. These are more connected with each other than across. You've got a group here, same higher connectivity within group, and then same there. So 3 groups. We're going to distinguish those groups by shape. Okay, so we've got circle, square, and triangle. All right. So 3 communities that we can see just due to connectivity. And within each group, those nodes are going to be more connected. Okay, so now for getting shape and looking at color, imagine we go in at each node and we take a measurement, we look at their covariates. So imagine maybe you've got 3 emerging groups for like the covariate measurements. So basically, if you were to go plot out your covariate measurements as points in space, you would get 3 clusters, okay? And this is sort of distinguished by color, all right? So we've got green, blue, and red. So basically, if I go to a red node here, that's going to be some red cluster mean, maybe plus some noise or something. That's what you would observe, all right? So all the measurements on all the red nodes, they're going to be roughly the same. And then same thing for blue and green, all right? Okay. Good. Cool. How do I construct like this one in particular?
Or in general, they use the same for in general.
You mean like software to like make it?
No,
Or-
no, what type
Oh, what type of graph? Mm, I mean, it's got weighted edges, so it's not binary. Yeah, I mean, I mean, if you're like familiar with it, it's the stochastic block model, but then there's also covariance. It's like a similar idea for it's basically like what stochastic block model would be for n by p data. That's the covariance. Yeah. Cool. So, all right. So yeah, now let's kind of take our model. I'll tell you how we're going to estimate these joint and individual components, and then we'll plot them and see kind of what information each one is captured. Okay. All right. So I guess can I move this out? Yeah. What's up?
Start this, do you have prior information about the group identity of each node?
No.
So that's figured out somewhere in the algorithm.
Well, so it depends on like what you want to do or like what you're doing. So like all this stuff is basically just maybe there is some group or community structure. We don't know it. Okay. Maybe it's not very apparent at the beginning either, but we're gonna send it through our method, and then maybe we'll see some nice clusters, or maybe there's no clusters. Maybe it's just got some nice interpretation as far as other relationships. But the idea is that like our method would be able to maybe make it easier to capture stuff like that. Yeah. I'm just giving you like the actual like community structure, just so that when we see, just so we can kind of talk about what information the joint and individuals are capturing. Yeah. Okay, so step 1, we need to extract the singular subspaces from our data. Okay, so let me kind of go to the board here. I think it's a little opaque, so I think it'll be a little easier if I draw some stuff. So remember, we have this signal plus noise model. Okay. And remember, our mean matrices, our signal matrices have a certain factorization, so we can write them as M R1 times some other stuff. And then the signal in the covariates, we can write it as M R2 times some other stuff. Okay. So the idea is like if you pulled the singular vectors from P here, you would get this one. You would get those. Those are the singular vectors. Or you might get an orthogonal rotation. But up to orthogonal rotation, these guys are the singular vectors. So what we're going to do is we're going to introduce these new matrices, our estimates. Basically, they're going to be estimates for these guys. So the idea is that V1 hat is going to be approximately MR1, okay? And then V2 hat it's going to be approximately M or 2. Just pulling the top singular vectors from A and pulling the top singular vectors from X. So that's the first step, extracting singular subspaces from our data. Does everybody understand like the kind of the idea? Okay. All right. So once you have that, what you can do is you can extract the joint, or like extract an estimate for the joint subspace. So what you do is you're going to take these two estimates for our singular spaces of the data. We're going to concatenate them. So we've got this U. So if V1 is approximately MR1, we're going to have approximately MR1 in the first part, and then when we concatenate that, we'll have approximately MR2 in the second part. Okay. So that's the heuristic. All right, and then to get the joint, you just extract the top singular vectors from this concatenation. So the idea here is that you've got your joint appearing twice. So when you write out the SVD for that, you're going to have a higher weight on the joint components. Okay, so those are going to be the top RM singular vectors. Okay, that's the idea. Any questions on that? Yep.
So you're assuming you know the rank.
You're assuming you know the ranks. Yeah, I mean, you can estimate them depending on your favorite. But yeah, right now we're just focusing on assuming the ranks are known. Okay, so once you have the joint, then you can extract the individuals. All you got to do is just take your estimate for the joint individual concatenation, project this onto the orthogonal complement of your estimate for the joint. So when you project this onto the orthogonal complement, the idea of the joint, the idea is that this would get killed, right? And then R1 and M are orthogonal, so that won't do anything. You'll just have 0 and then R1. Okay, so when you take the top singular vectors, the only thing with signal in here is the individual. So that's why that's the idea behind taking the top singular vectors after killing off the joint. All right. All right, cool. All right, so when we apply this estimation method to that network, that little toy example I showed you earlier, right? We had roughly, maybe I'll just take a peek here real quick. Okay, so roughly, again, just connectivity established 3 groups by shape, and then covariance established 3 groups by color. Okay, and notice that just with connectivity, you cannot distinguish the blue and the red triangles, right? And then, so that's like the network data set cannot distinguish that, okay? Similarly, the covariates cannot distinguish between this group and this group. They have the same color. Covariates can't see the difference, okay? All right, but what both data sets do, they can both distinguish between green and not green. They can both do that. They can also both distinguish between triangle and not triangle. Okay, so let's take another look here. So this is exactly, so what I just said, that's what's being captured by the joint. So the joint is capturing what both data sets can distinguish. Triangles and not triangles, green and not green. The individual components are capturing the individual components are capturing what one data set can do, but the other cannot. Okay, so since, for instance, the connectivity data set could distinguish between circles and squares, you'll see those come apart on the individual or the covariates, or sorry, individual for like connectivity. So network distinguishes. And then same for covariates. Covariates can distinguish between triangles, red, blue. So if you plot that part of the part of the components, you'll see that they distinguish. Okay. Everybody clear on what the joint and individual is kind of capturing? All right. So that's great. That's kind of what we would want. All right. So now that we've kind of gone over what the estimation procedure is, what it means, I'll give a little bit of theory that we came up with to talk about how good it is. But to talk about how good our estimates are, we need to talk about how far away they are from the truth. We're going to need a specific notion of distance to do that because we're really working modulo a orthogonal matrix, right? Okay, so for that, we're going to use the Procrustes distance. So the Procrustes distance is essentially just the best alignment distance between two matrices. So we're going to be talking about matrices A and B. For us, they're going to have orthogonal columns, but orthonormal columns. They're going to be bases. But yeah, the idea is just like, okay, we don't really care about how far the joint and its estimate is. We care about how far the best alignment is. Okay, so we're going to iterate through all the orthogonal matrices. We're going to find the one that gives us the smallest distance after alignment. Okay, all right, so that's our notion of distance. Now there's going to be some parameters that affect how well we can estimate the joint and individual components. So the first parameter that's going to affect this estimation is going to be the signals. So the eigen and singular values of the network and covariates, okay? And the smallest singular values. I'll just say you can do similar stuff if maybe if your data matrices are approximate, or if your means are approximately low rank, it would just require making some changes. But okay. So yeah, signal strength. The next parameter that has a really nice geometric interpretation is the individual subspace separation. So this is going to be the separation between the individual subspaces R1 and R2, script R1 and script R2. All you need to know is this is between 0 and 1. Okay, so 0 means that they're touching. 1 means that they're orthogonal. And let's just think about this for a second. Okay, so imagine that the individual subspaces are touching. This is the stuff that's not in the joint, right? It's individual. So if they're touching, that means there's something that's common to both the individual for the network and the individual for the covariates. However, that individual information is still contained in the original data sets. Like it's just a subset of our total information. So you've got stuff that's both in the network and in the covariates. So by definition, that should be in the joint, right? It shouldn't be in the individuals, okay? So that's why, first of all, the subspaces can't touch, okay? But imagine that the subspaces are like really close. Imagine that the true subspaces are really close. All right, when you like add some noise to your mean, all right, it'll perturb it. And that might make it look like it's touching and really hard to distinguish, well, what's actually joint, what's individual, all right? So the smaller this separation is, probably the worse our estimation is going to be. All right, and then sure, you've got some like variance type terms, right? So you've got kind of the standard deviation for the covariates. Like for us, we're using is like each entry in the covariate matrix is going to have some standard deviation. For us, it's going to be IID, but anyway, just loosely speaking, variance is going to affect that. And then you're going to have a variance type term for the network. So we'll just call it kappa. The takeaway here is that this variance type term for the network, it's for the tail. probability of the spectral norm of the noise for the network. And you just need it to kind of fall off sub-exponentially. Okay, it needs to be sub-exponential. All right. Okay, so once we have these parameters, I'm just gonna introduce some notation to kind of collect some of those. So first off, we've got this noise term that we can associate to the network. It's going to be the variance type term over the signal, and then times some rank. Similarly, for the covariates, we've got a noise level type term. All right. So I'm just collecting parameters here. All right. And then here's a theorem that we came up with. So basically, if you've got a sub-exponential tail for the network, for the spectral norm of the network noise, and your covariate noise is IID sub Gaussian, then on average, the procrustes distance between your joint and your estimate for the joint, it's basically going to be inversely proportional to the subspace separation and proportional to those noise levels for the network and covariates. Very, very close, almost the same thing for the individual subspaces, but there's another rank tacked on. So yeah, so basically, if we look at these epsilons again, the bigger the signal, the smaller the variance kind of associated to each data set. And then the bigger the separation between the individual subspaces, the better our estimates are going to be. Okay, sound good? All right. Cool. All right, so once we get that estimate through that spectral method I kind of went through on the board, we actually want to refine it a little bit further, because when you're taking these top singular vectors, you're discarding possibly some information in the data, right? Just maybe it's lower signal, but potentially kind of hurting. Okay, so what we can do is we can actually consider an associated loss that if we minimize that loss, it would give us a good representation for, say, like joint individual components in a way that doesn't discard that information. And if we could solve that, that would be great. Now the problem is, so like here's kind of the loss, right? It's basically exactly what you would expect. We come up with these sort of proxies for the network, but essentially you're trying to minimize the distance between like the means, the covariance and its mean, and the network and its mean, essentially. So just heuristically, as such that the structure respects how you were setting up the joint before. So the joint needs to be contained in their intersection of the mean parameters and have the appropriate ranks. Okay. Now this optimization problem, we don't have a closed form solution for it, but the idea is, why don't we initialize at the spectral estimate that we got that has theory, we can, under certain conditions, get consistency or whatever, start there, and then break this optimization problem into two related optimization problems, basically kind of like a block coordinate descent, where you fix the joint, locally optimize for the individuals, fix the individuals, locally optimize for the joint, and then continue until convergence. Okay. All right. So yeah, just wanted to kind of mention that. So that's kind of the full estimation procedure. Now we can take a look at some that real data set that I mentioned before. So again, we're going to look at the international food trade, and we're going to go measure at each country. We're going to go measure, like record the GDP per capita, geographic region, like birth rate, things like that. And then we're going to ask some questions. I put up a couple slides here so we can talk about like grouping, clustering, structure. Does having extra information help us get better clusters, or maybe other types of interpretation? What can one data set say about the other? Do we need both data sets, right? Are we getting anything extra by having both? Can we maybe use the covariates to see if there are sort of well-defined, better defined trade blocks, things like that? Okay. All right, so just kind of preliminary investigation into the data. We can do some PCA on the network. And so if you don't know what PCA is, basically just we're realigning the data and we're taking the biggest, like most important bits from that. But if we look at the PCA, I mean, I don't know about you, but if I got this data and I didn't like know anything else about it, it doesn't really look like there's maybe super well-defined community structure, and or maybe not a whole lot of interpretation. But if we look at the covariates that we grabbed, if we do PCA for the covariates, it definitely looks like there's better kind of community structure. Now, if you go in and look at your other data set, your covariates, you'll see that there's like pretty good like clustering based on geographic region. Okay, and that's just because I picked some extremely like some covariates that are very much affected by region. But anyway, point is there's better structure here. Okay, so maybe we can take advantage of that. And then I'll just make a note for later that I think it's like Asia here is the green and Africa's the red. So like the covariates can definitely distinguish between Asia and Africa. So I'll come back to that in a second. Okay, so when we run this data set through our method, I plotted the joint components from just the spectral method, and then I plotted the joint components after you initialize at the spectral method estimate, and then run that optimization. So we definitely get some better clustering structure in the joint components than we did in the PCA for the network. Okay, so there's better defined groups. First of all, you can kind of see that the optimization method did kind of tighten up some of the groups, so that's good. It's helpful. And then still, you just cannot distinguish in the joint. You cannot distinguish in either case Africa from Asia. That's the black and blue dots up there in the top left. All right. So those can't be distinguished, but the joint components can distinguish between every other region. All right. But in general, like maybe you're not talking about geographic, but just in general, we got some better defined clusters. I think some of those are Europe. I think some are Asia, like Kazakhstan maybe, or something like that.
But in that Asia cluster is China, Japan, and
Yeah.
South Korea.
Yeah. Although it doesn't have every country, so it may not have like see, I think one of the ones that it was missing. So like basically we had to grab data from two different spots, like UN World Trade Database, and then some other data set. And so you have to have like the countries present in both of those. So some of those didn't have it, but Most of the countries, yeah, right here.
So after recovering the community labels, how are you like validating your algorithm, like checking whether like in some sense that what you got was the true community label? Suppose you didn't have like geographical locations or something like that. So in case of two data sets, how are you gonna sorry, my knowledge in this is very little. So, for example, in multiple hypothesis testing, we do something like FDR, we check what the false discovery rate is, something like that.
Mhm.
So, what measure are you using to check how your method is performing?
Yeah, so this isn't a method for like community recovery.
Yeah.
That's gonna be like a later work.
Okay.
All this is doing is just identifying joint individual structure. But as a consequence of that, we're definitely seeing some clusters, like some clustering information being captured. Okay, but we haven't done that for like clustering specifically yet. That's in a later work. Yeah.
Okay, got it.
Yeah. Okay. So anyway, yeah. So we do see some kind of well-defined clusters here. And then just reminding us what this means. So these are the joint components. So the joint is capturing what both data sets capture, right? So that means, like, for instance, let me go over here. So, okay, if I take 2 points in the joint, in this plot, if they're in separate clusters, maybe it's not regional or anything, we don't know anything like that. But if we just know that they're in like sort of separate clusters, that means both data sets can distinguish those points. Okay. However it's distinguishing them, they can distinguish between both. And if you recall from before, we had 2 different clusters in the covariate data set that were basically captured by, it was capturing like regional information. But it was stuff from Africa and stuff from Asia. The covariates could distinguish between all those countries, but here they can't. Okay, so you can kind of introduce some like logic into it, and you know that, well, since the joint is what both can, and you know that the covariates could, but it's not happening in the joint, that means that your other original data set, the network, could not distinguish between those 2 points. Okay. And then kind of on the other side, the joint is distinguishing between, let's say, like this point and any point in here. So we know that in both original data sets, they could be distinguished. And then, so we've noticed some other stuff. Sometimes you'll notice like some trends, like maybe if you plot it by GDP instead of region, you could see some clusters that are capturing like increasing GDP or whatever other covariate you're looking at. So so I guess like the point is that just applying so here's our original PCA. No real good kind of maybe clusters. If we were going to look at maybe doing some k-means or something on here, it'd be maybe questionable, but we do know that there is some clustering information in that data set. It's just hard to see, and we can kind of filter it out a little bit when we integrate that with the other data set. Okay. All right, there's some other things you can ask, like can you identify, like can you quantify how much information in one data set can be like explained, or like how much variation in one data set can be explained by the other. So this is super easy. You can just partition your data sets. Like say we want to partition our network. Well, we can project onto the joint, we can project onto the individual, and then just have everything else. All right, so we've got this partition. These are all perpendicular to each other. And then just like in PCA, if you want to like quantify how much variation in the network is explained by the joints, well, you just take that part, right, and then find the Frobenius norm squared. So like the variation there divided by the total variation in the network, and that would give you the proportion of variation explained in the network from the joint components. You can define all these terms similarly for the covariates or for other components like the individuals. Okay? And so like what does this stuff mean? So if you, well, maybe I'll go back to here. So if you say have like maybe the variation in the network due to the joint, maybe that's really close to 1. What does that mean? That means that you can get this joint structure from the covariates. It's in both. So in particular, it's in the covariates. So you can use the covariates to extract some information that you can then use to isolate most of the variation in the network if it's close to 1. Okay? If it's close to 0, it's kind of like the opposite. The covariates would not contain very much. It couldn't explain very much variation in the network. Okay, and then you have like a similar interpretation for the individual components. Okay, but if you kind of calculate some of these, then this might be like a good pre-processing step. You might get an idea of, do we really even need another data set? Like if, you know, here, let's see, this is the variation in the network due to the individual components, and that's 80%. So most of the information in the network is actually like unique to the network, but it does share a little bit of overlap with the covariates. If you saw something in here that was like maybe 100% for like the joint or something, I don't know, maybe it would be a waste of resources to use both. Okay. Yeah, so anyway, it's just another way to quantify the information available to us in multiple data sets. Okay, so anyway, the take-home message is just that, look, we can partition our data, okay, in terms of what they have in common and in terms of what is unique to each of them. All right, and then this information may be helpful for sort of having a holistic view of the data that's available. Also, maybe talking about how one data set relates to the other. Maybe we can extract some sort of other structure, like clustering structure, something like that, or other. So yeah, so this was with 2 data sets, the network and covariates, node covariates, but you know, it's got pretty simple extensions to more than 2 data sets. Maybe you've got a mix of covariate and network. Maybe you've got multiplex network data, so just multiple networks on the same nodes. And then like, yeah, two clear like follow-up ideas are like kind of getting the cluster recovery rate and other things. So yeah, okay, well that was basically it. So yeah. Cool, thanks. Any questions? No. All right, what's up?
So can you go back to your like the results on the expectation of the distances between the 2?
Oh yeah, this one.
I might have missed it. Did the sample size play a role here?
Yeah, so it's the sample sizes captured in these epsilon terms. So it's not like super obvious, but I will say that like it's like under some kind of maybe simple assumptions, basically the rate kind of looks like 1 over square root n plus 1 over square root p. So yeah, definitely like the more data you get, more rows and columns, the better the estimation is going to be.
The lower helps too.
Lower rank helps as well, for sure. And yeah.
Could you go back to slide where you were explaining how to select the top eigenvector best process?
Oh, like the kind of the method, this, yeah.
So,
Oh.
yeah, maybe I'm just not understanding it right. So, basically you were interested in how to get a clustering which is dependent on the data and also the coordinates, right?
Well, we're interested in getting, not necessarily the clustering. That's like really specific. It's just like, I use that example because it's kind of easy to see with the plots, but like, you're just trying to get, in this first step, you mean? You're just trying to get like information associated with the network. That's like this V1 here. That-
And for the information, you are using like clustering as a tool to identify that information?
Oh, no. Clustering is like a potential application of having that information.
Okay. I
Yeah.
see.
Yeah, so the whole main thing is just getting like general like subspace information about these networks. But as a consequence of having that information, sometimes you can get extra interpretation, like maybe
So that's a
clustering function.
byproduct.
It's a byproduct. It's a
And-
byproduct. Yeah.
Thank you.
Yeah. Cool.
Thank you, speaker.
Yeah, thank you.